Welcome to Big O Notation, your guide to understanding algorithm efficiency. Before we dive in, here's a thought from computer scientist Donald Knuth. This quote captures the essence of why we need Big O notation. Let's start with a fundamental question. How do we compare different algorithms? As the input size grows, we can see that some algorithms slow down much faster than others. Here's algorithm A. It grows linearly with the input size. And here's algorithm B. Notice how it grows much faster, quadratically. The gap between them widens dramatically as the input grows larger. We need a simple way to describe this growth rate. That's where Big O notation comes in. Big O notation is our standardized way to describe algorithm complexity. It describes how the runtime grows as the input size increases. Let's look at the most common complexity classes. O of 1 is constant time. It always takes the same amount of time, no matter how large the input. O of log n is logarithmic, very efficient, like binary search. O of n is linear. The time grows directly proportional to the input size. O of n squared is quadratic. Time grows with the square of the input, getting slow quickly. O of 2 to the n is exponential. This gets very slow, very quickly. These are the building blocks for analyzing algorithms. Now, let's see these complexities visualized on a graph. On the x-axis, we have input size n, and on the y-axis, we have the number of operations. O of 1 is flat, constant time, regardless of input size. O of log n grows slowly. Even if you double the input, you only add one more step. O of n grows linearly. Double the input, double the time. O of n squared grows rapidly. This is where things start to get expensive. Notice how the differences become more and more dramatic as the input size grows. Let's see a real example, comparing two search algorithms. Here's our sorted array of 8 numbers. Our goal is to find the number 23. Linear search checks each element one by one, checking the first, second, third, and so on. Found it! That took 6 checks. Now let's try binary search. Binary search is smarter. It splits the search space in half each time. First, it checks the middle element. Then, it knows to look in the right half, so it checks the middle of that section. Found it. In just 2 steps. With larger datasets, binary search becomes dramatically faster. So, where does Big O notation matter in the real world? Search engines need incredibly efficient algorithms to handle billions of queries every single day. Navigation apps must find the optimal route among millions of possibilities in just milliseconds. Video games require real-time calculations for AI and physics to create smooth gameplay. Social media platforms sort through millions of posts to show you the most relevant content instantly. Efficient algorithms power the technology we use every day. Let's recap the key points about Big O notation. First, Big O describes the worst-case growth rate of an algorithm. Second, we ignore constants and lower-order terms. We care about the overall trend, not the exact numbers. And third, this knowledge helps us choose the right algorithm for the job, making our programs faster and more efficient. Thanks for learning about Big O notation with us today. Subscribe for more animated computer science lessons just like this one. See you in the next video.